We're going to look at the Fourier transform that's used in wave analysis extensively. We need the notions of wave number, frequency, a time domain, or a spatial domain. And you need to remember the notion of superposition. That is that you can add up a lot of different functions with different coefficients and get a new function. In particular, you would have seen a Fourier series where you add up sines and cosines with different coefficients to form new or to form any periodic function. So what I have here is an illustration that shows how a Fourier transform kind of takes a composite wave, a wave that's been made up of several bits. So that's this one here in red. You see that that's some periodic function. It looks roughly like a step function, an on-off. It's not quite because it's only made up of 3 different components. But when you do the Fourier transform, it breaks down into the first mode, if you like. So this is a sinusoidal wave of 1 period fits in there. Then you see that this is 1, 2, 3. And then you can do the same with this. There's more periods in there. You notice also that there's different amplitudes. An amplitude there, and that one's quite small. What happens is the Fourier transform you can think of as taking this red signal and returning this spectrum here. What you're returning is essentially the amplitudes of the different waves that you're superposing to get your original signal. The Fourier transform can act in time, as is the original purpose of the diagram. It goes from time to frequency, but if you've got space, you go from space to wave number. Okay, and as you have increasing frequency, that's obviously, decreasing the period of these waves, so you're fitting more of them in that space. Right, so that could be, you can think of it as increasing f, or the angular frequency omega, or the wave number k, depending on what your original wave physically means. Fourier transform doesn't actually care about physical interpretation. It is essentially just an integral. It's a special integral. Special in the case of rather valuable. But this is the definition of the forward Fourier transform as per our textbook. So it's integral over all of the domain. So I'm using t, which has the interpretation time usually. But I could obviously swap it out for x if I wished. So I could write So you can use this different notation. This is for a spatial function f. You've got a k. Let me just correct that so it doesn't look so terrible. You've got a k and an x instead of an omega and a t. That's all cool. All right. Now, what you notice with either of these definitions, and I'll just focus on the frequency and time version of the transform for now. What you notice is that you integrate away the t. So this is a definite integral, right? A definite integral with respect to t. WRT with respect to. And so once you've done this integral and taken the appropriate limits as t goes to plus or minus infinity, the variable is gone from your function. So what you're doing is you're essentially using this integral to get rid of the time variable. Instead, what you're left with is a new function which varies with omega. So that's why you can think of these transforms as being a map between a temporal domain and a frequency domain, or equivalently a spatial domain and a wave number domain. So okay. The interesting thing about the Fourier transform is how we go back, right? We often use Fourier transforms to, there's a few places they come up. One is numerical methods which simplify partial differential equations. If you take a Fourier transform, you can actually go from a differential equation problem in your original temporal spatial domain and get an algebraic problem in your frequency or wave number domain. So instead of solving a DE, you're actually just solving an algebraic equation, which is a lot easier to invert than a differential equation. So we need an inverse transform. So I'll just write ft for the Fourier transform. This takes g hat of omega and returns g of t. All right. So again, we're going to be integrating, except now we're going to be integrating omega. Now we know that we've got a scaling factor. We've multiplied up here by e to the I omega t. So what we're going to do here is multiply by minus I omega t. So that should, it's like the inverse operation. And we're going to integrate with respect to omega. Now, it turns out that when you do this, you don't actually get g of t back. You don't get your original g of t back. There is a factor of 2 pi which pops up from this e to the I omega t type thing that we're multiplying by. So in order that our forward and reverse transforms do not introduce a multiplicative constant, we divide out that constant like so. Let me just a slight quirk of the Fourier transform pair is that you don't actually have to define the 1 on 2 pi in the inverse transform. So you could equally define oops. You could equally define your Fourier transform pair like this, with the 2 pi on the forward transform instead of on the inverse transform. Another common definition is splitting that factor between the two transforms, the forward and the back. The last thing that's worth remarking on is that the plus and minus I can change as well. Just be consistent with what you use as your Fourier transform. Nearly always you'll be using, if you end up finding one of these Fourier transforms in the wild, you'll be doing it most likely numerically. You'll have a library routine that you'll just call, your program will call upon, and it will be using some numerical implementation of this transform called the fast Fourier transform. And for a start, that's a discrete transform, so it's ever so slightly different again, where the integral is replaced by a sum, but also depending on how or which library you're using and how the definition of the transform works for that particular Fourier transform algorithm, you're going to get different normalization constants, i.e. these things out the front. So just be careful that you understand the different definitions can exist. The definition that the textbook uses is this pair. So that's what we're going to stick with for future discussions. I think that's about all we need to talk about. So yeah, just be careful that you understand the differences between the notation and the definitions.